Laser ablation of metallic thin layers in liquids with wide irradiation spots. Charlottesville, Virginia, May, 2024. Let me start by describing our experiments. First, we evaporated thin films on glass and synthetic sapphire substrates using an electron gun in a vacuum environment. As measured by Rutherford backscattering, the total thickness of these films was 100 nanometers. The laser we used and its technical characteristics are shown here. The most distinctive parameter is the large laser spot, 6 × 7 squared millimeters. Here is a photograph of the experimental setup on the left, the laser spots in the middle, and the colloidal solutions obtained on the right. The nanoparticle concentration is very low, and unfortunately, we could not perform optical characterization. We tried to use the minimum necessary energy and the minimum number of pulses, which is a difficult compromise to achieve. Nevertheless, the repetition rate was 10 Hz, and we consider that incubation and fragmentation effects are negligible. Additional parameters for the two main laser wavelengths we used are provided in these tables. In this slide, you can see two electron microscopy images of silver particles produced in alcohol and water. As you can observe, uniform-sized nanoparticles were obtained, although some larger clusters were also present, as seen in the bottom figure. Throughout this series of experiments, we observed that nanoparticle growth is somewhat faster in ethanol. The results for platinum were more interesting, as many very large spherical particles were observed alongside smaller ones. Note that the diameters of these particles are much larger than the original film thickness. Platinum's high melting temperature might play an important role because a higher laser fluence is required to ablate the films, and therefore, more energy is transmitted and made available in the fluid. The observations were even more intriguing for gold, as seen in the following electron microscopy images. In these images, you can see some huge particles but also worm-like structures, nanowires, and nanocolas. Here, we have two additional comparisons between nanoparticle growth in water and ethanol. As I mentioned earlier, the processes are slower in water than in ethanol. Does the image on the left not suggest that the first structure is the precursor of the second one? On the right side, the second structure looks like a more developed version of the first. Initially, these results were confusing, but we gained insight when we found a reference where similar structures were observed in experiments conducted in controlled supercritical carbon dioxide environments. The laser is usually focused, and the spot is rarely larger than 1 mm in diameter. Since we used a much larger spot, we argue that the total energy available in the fluid is significantly greater. This leads to higher temperatures and pressures maintained for extended periods, significantly affecting nanoparticle formation and leading to the structures I have just displayed. A simple calculation using the heat equation shows that there is enough energy for the fluid to reach the critical point if the films melt before ablating into the liquid. However, realistic phase transition expansion and fluid dynamics must also be considered to estimate the pressure reached. Could supercritical fluids be forming in our case? We compare the critical point values for the fluids involved here to explore this idea. Let me tell you that our initial interest was in bimetallic systems. In the case of silver and gold films, we observed huge particles, as shown in these images, along with more complex and intriguing nanocollars that you can see in these electron microscopy images. An additional interesting example is shown here with a massive particle with long nanocollars attached to it. And here, you can see a group of huge, giant particles. Using high-angle angular dark-field imaging, we gained insights into the distribution of silver-rich and gold-rich zones. The structures are far from homogeneous. Let me admit that electron diffraction also confirmed the presence of silver oxides. It is important to note that the gold-silver system is completely missable. High-resolution images also allow us to distinguish and analyze different structures and compounds too. Here are a few images of the final system to discuss. Silver platinum. You can see large particles with smaller ones around and adhere to them. The analysis of single particles proved the presence of different structures. In this one, you can see platinum with silver oxide. We have also been interested in the intermetallic phase of silver-15 platinum-17, which is rarely reported in the literature. We found it in very small particles and volumes, though it is not the predominant structure. In this image, for example, we analyzed different zones and found that, with the help of the Fourier transform, the silver-15 platinum-17 phase is present. This phase is characterized by a large interplanar reflection. To conclude, I would like to highlight that evidence suggests that the liquid reaches supercritical states during and after irradiation in large volumes. We are still working with Navier-Stokes calculations to quantify these phenomena. Also, more sophisticated experiments are needed. And finally, that in the bimetallic silver-platinum system, the silver-15 platinum-17 phase is found in small nanoparticles. Thank you for your kind attention.